All right, so yesterday we finished up talking about molecular orbital theory, and we were drawing how these orbitals overlap when they're hybridized to form sigma and pi bonds. But one thing I wanted to do before we continue on is to compare some of these hybridized orbitals. So let's compare a handful of them. We're going to compare our hybridized sp3s to our hybridized sp2s. And last but not least, our sp orbitals. All right, which one do you think is going to be the longest? Meaning, which one can reach out its lobe the furthest? And why? sp3, why? Yeah, because it's 75% p character, right? So an sp3 lobe is 3/4 p. That means it's mostly dumbbell-like. If we think about sp on the other hand, it's only 50% p-like. So the longest one is going to be sp3, and then the shortest is going to be sp. All right, so let's consider this, right? Let's say we have a carbon-carbon versus a carbon-carbon double bond versus a carbon-carbon triple bond. Which one's going to be the shortest bond? Triple bond, absolutely. So it'll go shorter down here because it has little stubby lobes that have to overlap with one another. The longer ones are going to be the single bonds. Oops. So it is important to remember some of these trends. These will show up in spectroscopy as well. So when we get into IR spectroscopy, bond length and bond strength matters a lot because it impacts how they vibrate and move. All right, so that's kind of it for molecular orbital theory, but did anybody have any questions or want to go back and review anything? Oh, I know we went through this pretty quick, so if you do have any questions, please let me know. All right, next topic for review is bond polarity and net dipole. So let's take a look at a handful of examples. Let's do types of bonds, and I'm going to just do super generic types. The first one, if we look at it, is going to be ethane. It's one of the components of natural gas. Do you think this is going to be a polar molecule or a nonpolar molecule? Nonpolar. Carbon-hydrogen bonds are pretty nonpolar. They have very similar electronegativities. So this would be nonpolar covalent. And then we can go to something like methanol. I'll draw the full Lewis structure out. Methanol is very, very polar. Specifically, it's got one special type of bonding going on. Does anybody remember what that is? Hydrogen bonding, right? So this has hydrogen bonding. We would call these polar covalent. Or we could refer to this specific example as an example of a hydrogen bond system, or a system that can hydrogen bond, I should say. All right, and then last but not least, we could have something like sodium chloride. We don't like showing this as covalently bonded because it's not. They're not sharing electrons. It's more one's positive, one's negative, and they're attracted to one another. This would just be ionic. All right, in general, we try to classify these as best we can. There's some gray area in between them. In general, if you've got a difference of electronegativity less than 0.5, you tend to be classified as nonpolar covalent. So for example, if we look at an electronegativity table and we look at carbon and hydrogen, see carbon's 2.5, hydrogen's 2.1, difference of 0.4. That's not a very big difference. Therefore, this is an overall nonpolar system. Okay, and the next one though, we've got oxygen, which most of you are familiar with. It's pretty electronegative. And in this case, polar covalent bonds have a difference in electronegativity of approximately 0.5 to 1.7. So let's look at, for example, oxygen and hydrogen here. So oxygen is 3.5, hydrogen's 2.1, so that's a pretty large difference, right? 1.4 falls in that range of being a polar covalent bond. Ionic bonds, in general, have differences of electronegativity greater than 1.7. Because chemistry is confusing, there's all sorts of weird exceptions. Chemists like to push the boundary of what they thought was possible. There's even examples of carbon-hydrogen bonds that can actually be hydrogen bond donors that are very, very polar, but those are more the odd examples. This is just a general set of guidelines. Don't assume that this will always work. There are situations that fall outside of these. All right, so let's take a look at some examples here. So let's draw the following molecule. It's CH2Cl2. This is dichloromethane. This is commonly used to decaffeinate coffee. It's a really good organic solvent. So let's do the Lewis structure. Okay, so Lewis structure, we've got carbon in the center. You know carbon likes to form 4 bonds. We've got 2 chlorines, so I'll put it here, and I'll put it here, and then hydrogen here, and here, and just to be thorough, we'll throw in the lone pairs that are on the chlorines. All right, when we look at this, we know that chlorine's relatively electronegative. If we go back up to the table, you can see the closer you get to the top right-hand corner of the periodic table, the more electronegative the atoms are. Chlorine's relatively electronegative on there. So we could go down and we could look at this Lewis structure for dichloromethane, and we could say, all right, this is going to pull electron density away from that carbon. And in order to show this, you could also show the cross on the bottom. We'll talk more about those arrows in a second. And you could show it this way. On the problem of the day, I told you that if you've got dipoles pulling in equal and opposite directions, they will cancel out. Do these cancel out? Let's think about this more carefully, right? What aren't we considering? The hydrogens and the shape, right? We just spent yesterday talking about hybridization and shape. What's the hybridization going to be for this carbon? So the hybridization will be sp3, right? It will be tetrahedral. And the bond angles will be about 109.5 degrees. So we need to think about it as a 3-dimensional shape. So let's draw it in 3D. Okay, so the 3D representation will look much, much better. And if you remember, a wedge means that it's coming out towards you. A dash means that it's going back into the page. So now if we go ahead and we draw our individual dipoles, we can say really quickly, okay, we've got a dipole going up towards that chlorine, and then over towards the second chlorine. And then if we average the 2 dipoles, the net dipole is going to be pointed kind of in between those 2 chlorines. Does that make sense? They average together. In order to do this and predict net dipoles, you must know the overall shape of the molecule. You can't look at the Lewis structure and say, well, they cancel, right? That's not a fair representation of the 3-dimensional shape. Okay, so there are confusing methods for showing dipole arrows, so I did want to briefly talk about that. There's one method where you can use the arrow system like I previously did, where one side means that this is electron rich, meaning there's an electronegative atom pulling electron density towards the head of the arrow. And then the plus side means it's electron poor. So that's one system you can use to show dipole arrows. Chemists use this under certain circumstances. However, other times they use delta symbols. So lowercase delta with the plus sign means electron poor. And then if you've got a lowercase delta with the negative, this is electron rich. Tomato, tomato, you can use either system. Normally when we're showing dipoles, we like to use the arrow system, but occasionally you'll see people using the delta symbols instead. Does that make sense? Okay, so let's do a little bit of practice. Okay, the first thing I want you to do is to focus on BF3. I want you to draw the Lewis structure. I want you to draw the 3D structure. And then I want you to determine if there is a net dipole. And for your second compound, I want you to do NF3. So I'll give you a minute to work on this. Check with your neighbor and see if you agree. All right, let's do this as a class. We'll do BF3 first. That's boron trifluoride, Lewis structure. Boron only has 3 valence electrons, so we can draw it like this. Doesn't need to be super pretty, gets the job done. All right, so that's the first one. All right, now let's do nitrogen trifluoride. Nitrogen has a valence of 5. And it has a lone pair right there. And let's just be thorough and draw all of the lone pairs coming off of the fluorines as well, so we don't lose track of those. All right, if we think about boron right here, what's the hybridization going to be? sp2. What should the shape be? Trigonal planar. And it should have bond angles of about 120 degrees, right? So really the Lewis structure drawing that we have right here isn't the best drawing. A better drawing would be to have those fluorines 120 degrees away from one another, like this, each with lone pairs. This gives you a better idea of the three-dimensional layout, right? Is there going to be a net dipole here? Not quite. If we think about it, there are individual dipoles pulling electron density away from the borons, right? But they're pulling in opposite directions and canceling each other out. So that we would say no net dipole. All right, let's do the same thing with the nitrogen compound. Yeah?
So in earlier classes, you were talking about how we can, atoms like that, since it doesn't have a complete octet, can take in electrons from outside. Why aren't we doing that with this one?
That's a good point. So you're asking why we mentioned during our problem of the day that atoms that don't have an octet will frequently accept electrons and be good Lewis acids. This is a monster of a Lewis acid. It is hyperreactive. It very much wants to find an electron donor. Okay. So this is kind of an extreme example. You can study this in the gas phase, but if you mix it up with anything with electrons, it will immediately accept those electrons and form a new bond. Okay. We'll talk more about that when we get to acid-base chemistry. All right, now let's do the nitrogen. What's the hybridization? sp3. It has 4 electronic groups. So sp3. What shape? Let's be more specific. Trigonal pyramidal. All right, so it's not trigonal planar. It's almost like a little pyramid, if that makes sense. But it's not tetrahedral, technically. All right, so now let's draw the shape of this. So we've got one fluorine sticking out over here. We've got another one that's sticking out towards us, so I'll use a wedge like this. And then another one's kind of like another leg, and we'll draw lone pairs coming off of this as well, just to be thorough. All right, the lone pair is going to be occupying one of those sp3 lobes and just kind of sticking up into space, right? All right. We know fluorine is very electronegative, so it's going to pull electron density towards each of those legs. Is there a net dipole? Yeah, they're no longer canceling out. Where's the net dipole going to be pointing? Straight down. So it's going to average all of those, pull electron density down, and this one would have a net dipole. So like I said, understanding geometry is super essential. On a side note, if you haven't ordered a modeling kit yet, remember if you go under the useful links section of the class website, you'll see Darling models. You can get kit 1, 1A, 1B. They're all the same, they just vary in the box or container that they're shipped in. So you're welcome to get any of them. When we start getting into three-dimensional stuff, it gets really tricky. So you're welcome to buy those and you can use them on exams or quizzes. All right, any other questions? Okay, so let's talk about intermolecular forces. I know most people have seen this quite a few times already. Anybody remember the weakest intermolecular force? London dispersion. So we'll start with that. Some people will call this van der Waal forces. And some people will call it fleeting dipole. That's gaining more traction lately. Don't want to give the British more credit. Freedom fries. There we go. And this really comes down to the idea that electrons can't be everywhere at once. Pretty simple concept, but the way I like to describe it is imagine taking an imaginary camera, take a picture of an atom. You'll have a snapshot of where those electrons are at one time frame. So imagine you've got a helium atom. Helium has 2 electrons. It's got this s orbital kind of floating around it. There's a probability that both electrons could be on the same side. That means this side of the molecule is really electron rich, so we can use delta negative. And then this side doesn't have much electron density, so it's going to get that delta positive. If we have another helium atom nearby, it also, let me clean this up, also has an s orbital with 2 electrons, and there's a probability that it also has 2 electrons on the right-hand side in that snapshot. This side's electron rich. This side's electron poor. And now all of a sudden, you've got this strong attraction between the electron rich side of the left helium atom and the electron poor side of the right one, right? So this is a strong attraction or a stabilizing interaction, I should say. The interesting thing with these, though, is we know electrons aren't static. They move around a lot. So typically these are kind of weak interactions. However, if you've got a large amount of surface area, these weak interactions can add up to mean something significant. So let's consider this. More surface area equals stronger attraction. Another thing you can think about is more surface area typically results in a higher boiling point. And we'll talk more about that later. I don't really like it when textbooks call this super weak. The good example of London dispersion forces in action is Gecko Feet. Gecko Feet are actually mostly nonpolar bonds. But there's an incredible amount of surface area. If you zoom in on their foot, you can see this kind of fine, hairy network, and that's what allows them to stick to walls. It's that surface area and that attraction between 2 nonpolar surfaces that allows them to climb. Why do you think they don't want stronger interactions than that? Because they have to get their foot off, right? So it's kind of this delicate balance that nature's figured out. So let's go back to the surface area concept. And we'll consider isomers of the following molecule. We've got C5H12. Okay, so the easiest thing to do when you're drawing this is have one long chain of 5 carbons. This would be called pentane. We'll go over naming a lot, but in a few more weeks. and this has 12 hydrogens all around it. So that's one isomer. Alternatively, we could have branching. So maybe we've got 3 carbons. However, this carbon has 2 CH3 groups coming off of it. That's one option. Another one would almost be like a cross. All of these have 5 carbons and 12 hydrogens, though, right? What sort of isomers would these be? Constitutional isomers, right? So the other day we said constitutional isomers have a different structural layout, so the atoms are in a different order altogether. All right, which of these do you think has the largest surface area? Left or right? Left. The left one, if you think about it, it's almost like a spaghetti noodle. The one on the right is very, very compact. It's in a tight package. So that means that we would expect the one on the left to have the higher boiling point. Okay, when we go ahead and we experimentally test this, it turns out that this one has a boiling point of 36 degrees Celsius. The next one has a boiling point of 28 degrees Celsius. And then the last one's about 10 degrees Celsius. So you can see branching actually lowers the boiling point of compounds because it makes them a little bit more compact. People do wonder about this too. Why is that the case? You have to think about the full electron cloud around the molecules too. And the one on the right, the electron cloud, is just simply more compact. It has a much lower surface area to volume ratio. So it is mostly related to that surface area to volume ratio. Does that make sense? So consider branching when you're looking at boiling points. All right, the next one we're going to look at is dipole-dipole. These ones are also pretty common in organic chemistry, and these are interactions between molecules with net dipoles. Okay, so they're not instantaneous dipoles anymore. These are permanent dipoles. They don't go away. And we'll take an example here of acetone. Some of you might have used acetone to remove nail polish or use it to strip paint, things like that. And it looks like this. Where's the net dipole going to be pointing? Up, down, left, right? Right. Oxygen's way more electronegative. So it's got a net dipole pointing towards that oxygen. If we have another molecule of acetone floating around, I'll draw it in over here. It's going to look like this, and it's also going to have the same net dipole. All of a sudden, though, you've got an electron-rich side close to an electron-poor side. There's a strong stabilizing interaction. Okay, so that's pretty easy to remember. Net dipoles are attracted to one another so that the electron-rich side of one molecule is close to the electron-poor side of another. All right, there's a special type of dipole-dipole called H-bonding that most of you have heard about. So hydrogen bonding. What's the first thing that you must have in order for a hydrogen bond to occur? Hydrogen, okay. Easy enough. What sort of atom must that hydrogen be attached to? I always think of it as hydrogen being on the phone, so fluorine, oxygen, or nitrogen. must be on the phone. Like I said, there are exceptions to this, but this covers about 95% of the examples that are known. And then last but not least, you must have a lone pair that can be donated to that hydrogen. All right, so let's take an example, the easiest example. Let's do water. So we've got a hydrogen that's attached to oxygen. That works, so that's satisfying 1 and 2, and we've got a lone pair. All right, if we have another water molecule floating around, you end up with an interaction between the lone pair, which is the donor, the lone pair basically donating electron density to that hydrogen because that hydrogen is so electron poor, right? The oxygen stealing electron density from it. So this is a strong stabilizing interaction. All right, so most of you are familiar with that from either other chemistry classes or biology classes. Yep.
The oxygen is so electronegative. Why is the lone pair going to help out the hydrogen?
That's a good point. So any lone pair can participate. In this case, it's the only available one. So because that hydrogen's so electron poor, it just wants anything, and oxygen's there. And the other thing to consider, right, is this oxygen is really, really electron rich because it's hogging electron density from its own hydrogens. So it's actually not electron poor. Yeah. All right, so we can start classifying these in terms of relative strength. And I'm not going to go through all of the examples of intermolecular forces because they're kind of combos of the few we've seen. The first one we saw was London dispersion. Next one we saw was dipole-dipole. Then we saw H bonding after that. However, H bonding is really a special type of dipole-dipole. You can also have ion dipole. And then you can have ion-ion, meaning just an ionic bond in general, right? Which do you think will have the strongest interaction? Ion-ion, absolutely. So ionic molecules, if you try to, let's say, boil salt, are you going to have much luck? No, they have incredibly high boiling points. So ionic compounds really do not want to be ripped apart. Versus London dispersion, you can boil those at relatively low temperatures, assuming there's not an enormous amount of surface area. So this one is typically thought of as stronger. And then London dispersion is thought of as weaker. But like I said, London dispersion depends on surface area. The good example to kind of remember this is crude oil. Crude oil is almost all nonpolar compounds, but it has a very high boiling point because it's long chain carbons, right? So they go through a process of cracking that crude oil and making it into smaller chain carbon chains. All right, the other interesting thing that students forget about is when you're choosing an intermolecular force, you don't have to just choose one. In fact, oftentimes it's a combination of a lot of intermolecular forces. And one thing I always remember is that 25% of the attractive force in water is actually London dispersion. So dispersion does play a very, very large role in how organic molecules interact with one another. All right, so I'm going to give you a couple practice problems here, and I want you to help me predict which one will likely have the higher boiling point. We'll do CF4, carbon tetrafluoride, versus CCl4, carbon tetrachloride. And I want you to determine which one has the higher boiling point and why, and then talk about it with your neighbor. All right, give me a thumbs up if you have agreement with your neighbor. All right, let's go over this. This one is a little abstract. So carbon tetrachloride, if we think about it, is a tetrahedral molecule. Both of them are. So I'll go ahead and draw the overall three-dimensional shape. We know shape plays a large part in electronegativity, or net dipoles, I should say. Oh man, that looks messy. All right, is there an overall net dipole? I don't think so. They cancel out, right? They're pulling in opposite directions. So I would say no net dipole. What's the intermolecular force going to be if you have a jar of this between multiple molecules of CF4? Dispersion. All right, if we go to CCl4, it looks pretty dang similar. You've got 4 chlorines coming off of it, each with their own lone pairs. Is there going to be a net dipole here? No, it's practically the same. So we'd say no net dipole. This would also be dispersion. All right, which one will have the higher boiling point? It seems like we're kind of stuck. They both have dispersion. Anybody want to throw out an example or an explanation? What do you think?
Carbon tetrachloride because it's bigger.
Okay, so you said carbon tetrachloride because it's bigger and has larger surface area. I think that's a great answer. If you remember periodic trends, as you go down a column, the atoms get bigger and bigger. And like we said, when we're looking at London dispersion forces, surface area matters. People often will say mass. It's not mass so much as the surface area of the chlorines. So this one will have the higher boiling point. Due to the larger surface area. So there may be questions on exams throughout this term where I ask you to predict the relative boiling point. Just remember to kind of break it down, ask about the intermolecular forces, and then assess them from there. Yep.
So for surface area, is that only for dispersion, or does surface area matter for other forms?
So typically I won't give you super complicated examples. I'll give you one where you're only comparing one variable, for example. Does that make sense? Because it is hard if I'm throwing multi-variable things at you to know what you're dealing with. All right. Does that make sense for how to kind of predict boiling point? Let's do one more. This one I'll just draw up for you. We'll do formaldehyde. This is found in embalming fluid. Versus methanol. Which one do you think will have the higher boiling point and why? I guess we should take a step back and first ask, well, what's the main intermolecular force for formaldehyde? Can it hydrogen bond? It does have hydrogens, it does have oxygen, but the hydrogen is not coming off of the oxygen. So it doesn't satisfy the rules for hydrogen bonding. However, it does have a net dipole, I would say. So this one has dipole-dipole. All right, if we look over at methanol, this one does have hydrogen coming off of an oxygen. So this one does have dipole-dipole, but in addition, it also has H bonding. Which one do you think has a higher boiling point knowing that? The one on the right, absolutely. So this will have the higher boiling point. So make sure when you are looking for H bonds that you're double checking that you do have a hydrogen coming off of fluorine, oxygen, or nitrogen. All right, last but not least, yep. Don't worry about double or triple bonds affecting boiling points for right now. They do affect them to some degree, but we're not going to get into that right now. Good question, though. All right, last but not least, we've got to talk about solubility. So how well different classes of molecules mix. And the general term I like to use, I even use this in Chem 110, is like dissolves like. All right, so what I mean by that is solvents tend to dissolve solutes that have similar intermolecular forces. If you notice, I didn't say they have to have the exact same intermolecular force. They just need to be roughly similar in strength. So a good example of this would be trying to mix oil. So petroleum-based products are some combination of carbon and hydrogen. So I'll just write CXHY. What's the intermolecular force going to be for that? London dispersion. London dip, London dispersion, there we go. And water, we previously said, has H bonding. These are very, very different intermolecular forces, therefore these will not mix well. What do you need to do if you want to mix oil with water? I'll give you a hint. How many of you remember the oil spill in the Gulf? A few people. That was a really bad oil spill. They were trying to figure out how to get them to mix so that there wasn't an oily sheen. Essentially, the solution was to spray a huge amount of an emulsifier over the oil. And emulsifiers are kind of unique. What they do is they have one end that is attracted to water and then another end that is attracted to oil, and it will allow them to mix. Does anybody know something else that acts that way? Soap, right? So soap does that as well. We'll use a lot of emulsifiers in our organic chemistry labs. They're really common in green organic chemistry so that we can use non-organic solvents, right? So we can do organic reactions in water as long as we're using unique emulsifiers. Yep. Bile? I'm not sure, actually. I'd have to look that up. Yeah, I guess bile is, other people are saying. I'm not that sort of doctor. All right. The other thing to remember is that ionic compounds, what do you think they dissolve well in? Typically things that are either very, very polar, or even better yet, things that can hydrogen bond as well. So, like I said, they don't have to be the exact same intermolecular force. Yep.
Quick question. Is there one dispersion? Is it everywhere?
Yeah, so when you're looking at, you were asking, isn't London dispersion present in every molecule? And you're absolutely right. In this case, we're comparing the strongest intermolecular force feature for a molecule to the strongest intermolecular force feature of another molecule. Any other questions? All right, that's kind of it for Chapter 1 review. I know we flew through that. Please get started on sapling, and if you have any questions, don't hesitate to email me. I'm more than happy to help. If you email me at 1:20 p.m. before the quiz, I probably won't be able to help you. So try to be proactive with your questions.